Hey guys, hope everybody's doing well. So we're still talking about multiple regression, and I've talked a lot about a bunch of different stuff. We've built models, we've figured out what the regression equation is, and then estimated it. We've used Excel a little bit, and I've also recorded and posted a bunch of videos on practice problems. So what I'm hoping to do today, and eventually as we continue to work on this stuff, is to start changing the way that you think about math a little bit. I was thinking about this a lot recently. That the tricky part about math is that, well, we have gotten really good at using technology to do the arithmetic, which means that our job as people who are trying to learn math and use math to inform the way we look at the world and our analysis is really it doesn't involve numbers as much anymore. That's tricky because sometimes this stuff becomes kind of abstract, and that's when real math is kind of abstract. So what we've been looking at so far has been models like this, right? So let's look at a multiple regression model. That's a M, by the way, a multiple regression model, in which we have some variable of interest, some dependent variable y, on the left side, and it's equal to what we're doing when we build a model is we're asserting that there's some relationship between is x2 between y and our x's, beta k, xk plus epsilon. And so what we're saying is that this is the way the world is shaped, right? We're saying that there's some variable here, and this can be a lot of different things, right? This could be income, this could be happiness. They're trying to measure happiness now, right? It could be likelihood of heart disease. It could be lots of different things. And then these x's are lots of other things, right? It could be, I don't know, years of education or whatever. They're variables that we care about. But the ultimate thing that we're trying to do here is we're trying to build a model of a relationship. And we don't know what that relationship really looks like, right? What we're doing really is we're just sort of we're building a frame. This model is like a framework, right? We don't know what those betas equal. Those betas are our population parameters, and we've been talking about population parameters for a long time, because when you think statistically, what you're really kind of saying is that there's some relationship in the population. And the population, if you recall, is the kind of overarching outside world. It's what's really going on, right? We want to know how to make more money or how to be more productive or how to do things of use, right? Maybe not even things of use, but how to, best engage our leisure time, whatever. We want to know how to do lots of things, how to raise healthy kids, right? And all this stuff. And lots of things that we care about, we can use statistics to try to analyze, because statistics involves taking a look at the outside world and then thinking about it in a particular framework. These betas are governing this relationship, and I'm going to show you just a few models in words to try to drive this point home, that this is what the real math is. It is learning how to think about and manipulate these things, right? So a little while ago, we looked at a situation in which we had rent, right? Rent depended on the city that you lived in, right? The one that I proposed was New York versus Little Rock, Arkansas, because Little Rock is where I am, and New York is where the New York Mets play, which is my sad destiny to be a New York Mets fan. But so rent depends on the city. It also depended on floor space, right? Clearly, it might depend on other things, but we can just look at these two things, right? And there are lots of ways to try to posit, by posit I mean to assert, to claim that these things are related, and that's what I'm going to try to show you here, right? So we want to know about rent, right? That's why, I don't know, maybe we're being a consultant for a property manager, but we might say that, well, rent is equal to a baseline rent, right? Which is just sort of like a fixed fee. Even if you don't have any square footage, right? You have to pay this baseline rent plus the cost per square foot times the number of square feet. And in this model, and then there's some noise, right? Some error term plus noise. And that noise captures everything that's not in our model, right? And in this model that I've just built, and this is a model, I don't have the betas and stuff in here, but I'll show you how they correspond because they do correspond. In this model, we essentially have eliminated the city, right? This was the first model we estimated back then. We're saying that rent is some baseline rent plus a cost per square foot times the number of square feet, and then there's some noise. That's what makes it, if you recall, that's what makes it a stochastic relationship. Stochastic. It's not deterministic. You can't just plug stuff in because there's also this noise, this fudge factor that gets built in. That's what makes statistics. That's statistics, right? That's how we use our statistical reasoning. Okay, that's one model, but we thought that might be bad. What might be different? Well, maybe there's a rent that's equal to the baseline rent for Little Rock plus a rent premium for being in New York. Maybe there's a rent premium. And that could be positive or negative. I'm assuming it's positive because I know that rents in New York are higher. Plus, and then once that rent premium is covered, that's like a fee to get into the city of New York to get a place there, right? Like a finder's fee or something. Plus the cost per square foot times the number of square feet. It's a SQ square feet plus noise. And this is a different model. Okay, now we've incorporated our city. But notice that where the city comes is just in this, there's a baseline rent for Little Rock and there's a rent premium for New York. So you either have to pay the Little Rock fee or the New York fee, which is the Little Rock fee plus a rent premium. And then once you into that market, then you just pay for square footage like it's fixed, right? There's a multiplication sign times the number of square feet. And then there's still a noise factor that makes it statistical. Another model that we might look at looks like this. Rent equals baseline rent, which is independent of city, plus cost per square foot in Little Rock, times number of square feet, plus square footage premium for New York, times number of square feet. I'm running out of space. I need to zoom out or something. In any case, you can see what we have going on here. Let's break this down. I'm going to change color so I can break this down a little bit more because we didn't look at this one really. But here we have a baseline rent that doesn't matter which city you're in. It's independent of city. It's just a fixed finder's fee for getting into the rental market, right? You know, whatever that is. And then what we're saying here is that, well, there's a cost per square foot in Little Rock times the number of square feet. You got to pay that. And then there's a different premium, right? So you can think of the cost in New York as being the cost per square foot in Little Rock plus the square foot premium, both of those times the number of square feet, plus some noise. Now, this is kind of messy and noisy. We don't, this is not a simple way to write this stuff. You notice that I'm running out of space. This is why economists and statisticians and econometricians and all sorts of people who work with this stuff, anthropologists, everybody does statistics. But when people do statistics, when people do regression, they write this stuff a little more simply. So I'm going to rewrite these models using the Greek letters just to show you what these turn into. Now remember, we have our variables, kinda. Let me define a dummy. I'm going to define nydum as a variable, which is 1 in New York and 0 in Little Rock. nydum. It's just for the purposes of brevity. And this is what these models turn into when we translate them a little bit into math. Okay. Clearly, this isn't exactly English, but it's not so mathy. So let's look at this one. Rent equals, this baseline rent is the rent if the square footage is 0. And there's no noise, right? That's what we get. So if this square footage is 0 and there's no noise, this is going to be our intercept term. That's what this is. So that's beta 0. That's our baseline rent. Okay. Now what we have now is we have a cost per square foot, which is going to be our coefficient on square feet. And that's what beta 1 is, right? So this is this. Beta 1 is our cost per square foot times our number of square feet. And then our noise is epsilon. And that's this model. It is this, right? I'm going to write another model in a minute that's not related to rent that looks a lot like this, because it turns out that one of the reasons we use this framework, a statistical framework, is that you can get a lot of mileage out of simple stuff, right? Because we can simplify this even further if we want to. If you're willing to go the last distance, this is just y equals beta 0 plus beta 1 x1 plus epsilon. And x1 just happens to be square foot, y happens to be rent, beta 0 happens to be baseline rent, beta 1 happens to be cost per square foot. Epsilon is always noise. But you have to translate in your head from this model, right, which is very abstract, right? It's just y's and x's in Greek letters, to this, which is what we're really talking about. And if we can get really good at this, and this is, you guys are just getting started probably if you're watching this video, then it shouldn't come naturally yet. It takes some time and practice. But when you get really good at this, what happens when you see this y equals beta 0 stuff, you see this as rent, plug in rent for y, or I say, let's let y equal rent, let's let x1 equal square foot, and then when you get good at this, you start to say, oh, well then beta 1 must be the increase in rent from an additional square foot. That's the per square foot cost, right? That's what that is. You can think this should be marginal cost, by the way, not average cost. Okay, let's do this model. Well, here we have rent equals, and now in this case, because of the way we've defined our dummy, beta 0 is going to be the baseline rent for Little Rock, and then we'll add our square footage, beta 1 square foot, and then beta 2 times ny dum. Well, this beta 2 becomes the rent premium in New York. And we have our error again. It's a little bit, yeah, it's a little messy on the screen, but let's see. Let's talk a little bit about this model quick, right? So beta 0, we already talked about that. That's the baseline rent. But now because we have an extra intercept term right here, this just gets turned on and off. Remember, ny dum is equal to 1 when you're in New York and 0 when you're in Little Rock. Talked about this a little bit in the other video, but I just want to give you kind of an idea of how we turn this in, how we move from thinking about one model to something else. This rent premium then is something that only exists when you're in New York and doesn't exist when you're not. And that's what beta 2 is. Beta 2 only exists when you're in New York and doesn't exist when you're not. So that's how we turn that on and off. This beta 1 then is still the cost, it's still the marginal cost per square foot, right? It's how much you have to pay for each additional square foot. And that's right there. That's how we interpret beta 1. Once again, what this becomes is a much simpler model. Y equals beta 0 plus beta 1 x1 plus beta 2 times d2, where the d2 is just the dummy, plus epsilon. And this could be, y could be income based on years of education and gender. X1 could be years of education, D2 could be gender, and then beta 2 would be the difference, the difference in gender, that it would be the gender gap in pay, right? Y could be, I don't know, what do you think? Anything. It could be anything. It could be return on an investment, right? It could be return on an investment based on the X1 being, the previous year's return, or previous or Morningstar rating 1 through 5 stars, and D2 could be whether it's a blue chip or not blue chip, right? You can do that. You can throw those things in there. And this model, y equals beta 0 plus beta 1 x1 plus beta 2 d2 plus epsilon, can capture all of those relationships. Then you plug in the data and use the same estimation procedure to get that. All right, let's look at this last model that I drew up here. Okay, now here we have rent equals baseline rent, but now we have a difference in the way in which the city is incorporated. So let's rewrite this model. Rent now is going to be beta 0, which again is our baseline rent. In the last model, it was the baseline rent for Little Rock, but now there's no difference between rents, baseline rents, right? The kind of fixed cost of getting into the rental market. Now we have beta 1 x1, or beta 1 square foot. Sorry, I'm not to x1 yet. Beta 1 times square foot, and again, this is the cost per square foot, but now it's in Little Rock, because what we're going to do is we can add another thing that we want to be just a premium for New York. Beta 2 times square foot times ny dum. And what this does is it turns this term on and off, turns beta 2 on and off when you're in New York. But that beta 2 will be multiplied by the square footage plus epsilon, which again is our noise. So what this allows us to do is, instead of up here where we were modifying just an intercept term, here we're modifying a slope term. And with our models, we can do lots of stuff like this, and that's the beauty of using models to try to think about these things. It's why we want to start moving slowly but surely from these purple. And you should, to be fair, you should always start with something like this, and you might even want to write it out in a paragraph. I think this is really dependent on this, and I think it's dependent in this particular fashion. But then you can work your way to a model, and usually you'll find that that regression is very powerful. It's very easy to take, and in a video very shortly, I'll talk about how we can take situations, models from other disciplines, from economics or from finance or from accounting, from all sorts of places. We can take lots of different functions and linearize them in a way that will make them amenable to multiple regression, at least for linear approximations. Multiple regression is really powerful. But little by little, what we want to do is get better at going from this line down to the bottom line here. Let's turn this last model into a more abstract version. Now we have beta 0 plus beta 1 x1 plus beta 2 times x1 times d2 plus epsilon. This here is called an interaction term, and it allows us to adjust the slope interaction term. All right, that is a very full screen. If you've been walking along, I hope you can follow it. The more you work on this stuff, the more we think about this stuff, the better we'll be able to follow it. I highly recommend you take a look at the videos that go through applications. But what I'd like to do is, in the back of your mind while you're watching the other videos that kind of show you how to work these problems out and how to try to apply this stuff, is to start thinking about how you can move from a description of the world in words to a more abstract mathematical model. Because as we're moving along, as we're getting better at this stuff, and as we're capable of applying the power of the computer to try to do the arithmetic for us, we're really doing real math now in a very different sense. And this right here, this is what real math really turns out to be a lot of the time, is figuring out how to take a relationship in the real world and then turn it into something that we can tell the computer to use. And that's what this is right here, right? We know what our y is, we know what our x1 is. This x1 times d2 tells us something about what we have to do in Excel. It tells us that we have to create a dummy variable, right, that switches on and off with New York. In fact, this would be very valuable. I will just pull up the data and you can see what this looks like. Because I made up this data, it doesn't really exist. But I'll show you what that tells us. So, there we go. Paste this data. There we go. We have city, floor space, monthly rent. And this is the model. This is the very abstract model that I'm going to draw up here. It is y. Let's not write it there. Let's write it down here. Y equals beta 0 plus beta 1 x1 plus beta 2 times x1 times d2 plus epsilon. So that's the model we want to estimate. What we need to know is that our rent is our y, whoops, and our floor space is our x1. Okay, now because Excel can be kind of a pain, it needs you to have all your x's next to each other when you run a regression. So I'm just going to copy and paste this right over here so that we have it over here. Because it needs you to have your x's all contained in like a nice convenient block. We also want to have our dummy. We're going to need to create a dummy here. So I call it ny_dum. We can call it ny_dum, that's fine. It's going to be if this equals ny, value of true is 1, value of false is 0. Alright, clearly we could have just done 1, 1, 1, 1. By the way, what I did there, once I did it once, you just need it to be the same. Now you can copy and paste it all the way down, or you can just select all of these. If you hold Control Shift up, it'll select all the way down, and you hold Control D, it fills it all the way down. Okay, now we have our dummy. Well, now what we want to do is we want to create our interaction term. So I'll call this ny_dum x square feet. That's our interaction term. And this is just going to be this. It's going to be floor space times our dummy. And there we go. That's what we have. I'm realizing now that Excel's not going to let us, if we don't want to throw the dummy in there by itself, Excel's not going to let us do that. So copy this one more time, and now let's run the regression and see what we get. Okay, let's estimate this model. Go to Data tab, click on Data Analysis, go to Regression, click OK. Our Y's, let me pull this up here so you can see it. Our Y's are the rent, and our X's now are going to be the interaction term and floor space. Actually, if I estimate it like this, it's going to switch these around. So let me move this over here. Sorry. Y's again are rent, and our X's are floor space, and New York dummy is that the interaction term. And what we have is rent equals square feet interact. I'll just call it that so we know what it is. We did include the labels. I'm going to put it in a new worksheet, and that looks fine for now. These are residual plots. We have problems with our residual plots. That's okay. Now what do we see here? Well, you can see whether these are significant or not. It looks like our interaction term sucks up most of what we have going on. New York dummy x square foot seems to be capturing most of this, and what we might, in any case, what this is saying is we still have a negative relationship. That's not good. This is probably not a very good model. And what this model is doing again is it's forcing us to put the same intercept, right? If we go back to here, we just do a straight up scatter plot. Insert scatter. You can see that what this new model does, the B0 here, it forces them to have the same intercept, but to have different slopes. And so you can think of it as trying to pick a place here and then put lines that go through both of these, right, at different slopes. And essentially what this is saying, I think, is that, what this is definitely saying, this is the rate for Little Rock, and it's saying that Little Rock has a negative relationship, right, because that's the interpretation on that one. The interpretation on this one is that this is the square foot premium in New York, and that's very high. What this is saying is if we have to peg a relationship here, it's going to be somewhere like here, and it's going to slant slightly downward, and then it's going to be somewhere here and slant very much upward over here. The problem is that this is a bad model. That's what this is. We can estimate a better model by just including an intercept dummy, because clearly because I made up this data by setting the intercept to be different. But we can tell that by looking at our results, right? We can interpret this as it's saying that there's a negative relationship for Little Rock, and then that the rent for New York, the square footage rent for New York is this plus this. It's about $1 per square foot for New York, assuming that you start at 1746 for nothing. Anyway. It doesn't have to be a good model. The upshot is that it is a model that we built, right? And it tells us what we have to do. We needed to have x1, which was our floor space, and we need to have x1 times our dummy, which, let me move this out of the way. x1 times our dummy was right here. And so we did that, and we created that. We used the math of the situation to try to posit what the world might look like, and then take a look at it. A better model, I'll do one more model and we'll call it. A better model might be one that would include the dummy twice, right? Where we can estimate different interaction terms, or a dummy term and an interaction term, right? We're essentially then estimating two different regressions. Look at this, beta 2 d2 plus beta 3 times x1 times d2 plus epsilon. Now, in some sense, this is bad. I only have clearly this is not what you would really want to do. I now have 3 variables for only 12 observations. Or 13 observations. That's a problem. But for demonstration purposes, it's fine. Okay, so what do we want? Well, we want floor space, New York dummy, and that's going to be our right side, floor space, our New York dummy, and then our interaction term. That's x1, d2, x1 times d2. And then on the left side, we have our rent. So let's estimate this equation. Minimize the ribbon. Get ourselves a little more space. Data analysis, regression. Our y's are the same. Our x's are now going to be all 3 of these. Equals square foot ny dum interact Rock. Okay. All right. Now this allows us to have two different intercepts. This is the Little Rock intercept, and these two combined. This is the New York premium now. This is the New York rent premium. Is that $2,001? So 2,100 is the intercept for is our estimated intercept for New York right there. Those two added together, which shows up in the bottom right here conveniently. But then we also have a relationship between square footage, which in this case is 0.59, 0.60 for 60 cents per square foot for Little Rock. And in New York, it's almost nothing, right? And it's not significantly different from zero. That's because the way that I constructed this data, I just used the same square foot price for both cities. In practice, that's almost certainly not the case, right? If you were working with real data, this model would give you different intercepts and different slopes, and it would use the data. You can see that again. This is a really ridiculously high R squared because I'm basically just that's how I generated the data. But yeah, that's how you would estimate this model, and that's the important part here is that we have two models here that we've developed. One in which we have an interaction term and no intercept dummy. Here we have an intercept dummy and a slope dummy, and we've included both of those. But yeah, the more you play with these models, the more you start to think about what the implications of, the implications of one particular approach versus another particular approach, and how you take the real world and make it fit something that we can use Excel for. So there you go. That is just a little bit more of a description and kind of some intuition on how to think about the models. Next time we talk, I'll talk about residual plots, although you can already take a look at the problem with light rail. The light rail problem talks about that briefly, and then we'll talk about f-tests of joint the f-test of significance of additional variables. If you have any questions, as usual, post a comment or shoot me an email at jjdelaney@ualr.edu. Hope you guys are well. Bye.